welcome to RF transceiver design course. In last few lectures we have discussed enough about the mixer design and how different types of mixer, active and passive mixer we can design, that we have already discussed. In this lecture now we are moving towards the oscillator design. So, when we think about the oscillator, what are the performance parameters that is important for the oscillator design? So, first parameter is the frequency range. So, if you see, there is here one example is given where if you want to design a transceiver and for receiver here, the standard 11A TRX or for standard 11BG. For standard 11BG the frequency is around 2.4 to 2.48 gigahertz, and for 11A it is a 5.8 to 5.8 gigahertz. So, your oscillator should have a range which is which should include the all the requirement of the receiver. So, that is the one of the performance parameter for the oscillator. Another is the output voltage swing or the power. Oscillator is going to drive the mixer or the divider. Mostly divider is digital circuits, and mixer also required the digital input or very high output voltage swing, so that both the transistor we have already seen in LO will not be on, and there is a feed through will be removed. So, it should require a very good voltage swing and power for the at the output of the oscillator. Then third is the drive capability. Because oscillator is going to connect with the multiple modules, where here you can see that it is connected to the divider and it is connected to the mixer. It should able to drive the sufficient capacitance at output, and that can be improved by adding the buffer or some circuit which will help to drive a high capacitive load. Fourth is a phase noise. We up to now what we have considered that omega naught is nothing but a delta signal omega naught, but in reality oscillator has many other frequency component around that omega naught, and that has a behavior something like this. So, these additional frequency components are nothing but a noise, and it is denoted as a phase noise. Then output waveform, we already have discussed different type of duty cycle requirement for mixer design. So, duty cycle is also important. So, it should have a, if it is requirement of a 50% duty cycle, it should have a 50 percentage, so that the divider and other circuit will provide this sufficient duty cycle. It is also have a supply sensitivity, because if the supply is if supply is changing, if there is some variation in the supply voltage, it might add the phase noise, or it improves change the frequency of oscillation. So, supply sensitivity is also important, and power dissipation, because this is a power hungry components, and we can make sure that the design oscillator is not consuming lots of power. So, now we go back to the undergrad level and see that how the oscillator works. So, what are the condition to have a oscillation? So, if we consider this is a Hs transfer function that is connected in the feedback form, and it is adding a negative feedback. So, in order to have a oscillation, there is a Hs which is S is equal to j omega 1 equal to 1, and H angle should be 180 degree. So, this is called a frequency phase shift. This is a frequency phase shift, and this is a DC phase shift. So, total phase shift should be 360 degree. So, either it should have a total phase shift of a 360 degree, or this is a frequency phase shift which is 180 degree, in addition to the minus sign which is a DC phase shift is 360 degree. So, you all know this is nothing but necessary but not sufficient condition, that is a Barkhausen criteria. So, what is that? That uh, second criteria as a total phase shift of a 360, and loop gain typically should be at least 2 or 3 times of the required value. So, this is a Barkhausen criteria, and it needs to be this criteria needs to be satisfied in order to start the oscillation, and in order to sustain the oscillation this gain should be greater than or equal to 1. So, that is why it is mentioned 2 or 3 times. If we consider the total phase shift, it is a 360 degree phase shift. So, there are 3 means it is mentioned as a second Barkhausen criteria, but it is how you are looking at the circuit or topology, that in the first there is a DC phase shift is added due to the negative feedback, and 180 degree is added by the amplifier. In the second DC phase shift is considered positive, and total is a 360 degree. That is why it is also mentioned in multiple literature that oscillator has a positive feedback, and we can also consider it as a 0 degree, total is a 0 degree phase shift. So, as I told, there is a frequency dependent phase shift which is a 180 degree. This arrow is showing the frequency dependent phase shift, and this DC phase shift we can see here denoted at the adder. So, total phase shift requirement is a 360 degree, and there is a no phase shift at omega naught is provided. So, this is a Barkhausen criteria for achieving the oscillation. Now, this is a first example that can this circuit oscillates. This is what we can question, is it satisfying the Barkhausen criteria. So, if we try to see here that can we discuss that does this circuit oscillate. So, the answer is it is open loop circuit of a single common source stage contains only one pole, and maximum frequency dependent phase shift is a 90 degree at a frequency of infinity, because it has a one pole and that is have a phase shift of 90 degree at infinity. And if you connect the output to the input, DC phase shift is 180 degree. So, total phase shift is a 270, which is a less than 360. So, it will fail to sustain the oscillation growth. So, what is the next solution? Can you think of next solution? We can add another stage. Now, we will add another stage. Now, will this will this sustain the oscillation, or it is satisfying the Barkhausen criteria? So, if we see here in this circuit, there is a positive feedback, because this is minus minus plus. So, that is adding a positive feedback, and the total phase shift is frequency dependent phase shift is a 180 degree. Two significant poles appear in the signal path, and signal inversion through each common source stage. So, that is a positive feedback, and that is why it is a simply latch ups rather than oscillates. It is in order to sustain the oscillation, you required one more negative, instead of positive feedback you need a negative feedback. So, now we will add one ideal amplifier with minus 1. Will this oscillate? This This is providing a negative feedback near a 0 frequency and eliminates latch up. It has a two poles, one at E, means at one at E point and another at F point. Does this circuit oscillates? No, these circuits do not oscillate, because at infinite frequency, if you see this omega Pe, which is equal to omega Pf, because of that there is a minus 40 dB per decade slope. So, frequency dependent phase shift reaches 180 degree, but means if you see here it will reach to 180 degree, but at very high frequency or it is at infinity. So, loop gain vanishes at very high frequencies and the circuit does not satisfy both the Barkhausen criteria, because you are getting a phase shift, but it does not have sufficient gain to sustain the oscillation. So, it fails to oscillate. Now, that is why we are adding one more stage, that is a third stage of the amplifier, and when we are adding this, if we have a 3 stage, we can have a 360 degree phase shift at a desired frequency omega. So, here if 3 stages are identical, total phase shift around loop is minus 130 pi, or at omega is equal to omega Pe or Pf or Pg, it is 270 at omega is equal to infinity. So, if we want 180 degree and we want to have a loop gain greater than 1, that is possible in this ring oscillator. So, that is why we will have a 3 stage that will provide the complete, which is satisfying the Barkhausen criteria, and because of that we are using a 3 stage to have the oscillation. So, if we want to find the what is the amplitude requirement and the at this or what is the oscillation frequency, what we can do is, for 3 stage ring oscillator, here denote the transfer function. This is a transfer function of the each stage, that is minus A naught by 1 plus S by omega naught. It has a one pole, and total loop gain, if we multiply all 3, it is minus A naught cube divided by 1 plus S by omega naught whole cube. So, the circuit oscillate if each stage contributes the 60 degree of phase shift, because 180 degree phase shift that is required. So, tan inverse omega oscillation by omega naught, which is equal to 60. So, you will get omega oscillation equal to root 3 into omega naught. So, omega naught, if you want to design the oscillator at certain frequency, if you know the omega naught, you know the pole, and by choosing that values you can find out the you can size the your oscillator. Now, what is the gain you required? So, minimum voltage gain per stage is A naught. So, if we try to make it is equal to 1, this Hs is equal to 1 A naught cube by this, where omega oscillator by omega naught at oscillation frequency it is a root 3 omega naught. What you will get is a naught which is equal to 2. So, you need each stage should have a this much gain, and your oscillation frequency is equal to root 3 into omega naught. So, this is how you can design the ring oscillator. This is a widely used and simple architecture to design an oscillator. So, this is a waveform of a 3 stage ring oscillator. Now, each stage you can see VE, VF and VG. So, this if you try to plot at VE or VF or VG, each stage contribute frequency dependent phase shift of 60 dB and DC signal inversion. Thus, the waveform at each node is a 240 degree or 180 degree out of phase with respect to its neighbor nodes. So, if you required a different kind of phase shift, you can tape it out from different place, or you can use some other circuitry, digital circuitry to generate the other phase of the signal. So, this is how we can design a 3-stage ring oscillator. Now, we are moving to the other uh, kind of oscillator, and in order to understand that oscillator, we will see the one port view of the oscillator. So, what is this mean one port view of the oscillator? Now, you have a ideal inductor and capacitor which is required to generate the oscillation, and this is nothing but well known tank circuit. Here it is denoted as a inductor as a L1 and capacitor as a C1. If you just apply one pulse I naught of the current, then that current will uh, generate the voltage, that is around I0 by C1 V out. If we try to plot the V out, it will generate a voltage I0 by C1, and that voltage will start the current, because of this pulse and voltage form, the slowly start current will start flowing through the L1, and that current means will reduce the voltage across the capacitor. It will reach to this, and again it will reduce that whatever current which is charged at L1 will apply to the C1 voltage, it will generate increase the voltage. So, what will happen that initially the capacitor will charge, then inductor will charge, capacitor will discharge. So, the charging and discharging of inductor and capacitor will happen, and it, if you see the output voltage, it will sustain the oscillation. And what is the oscillation frequency? That we all know, that is omega naught is equal to 1 by under root L1 into C1. We can get the oscillation frequency by this equation. But in reality, we do not have a ideal inductor or capacitor, it always add a loss. So, we need to denote it with the resistance Rp, which is parallelly connected to the tank L1 and C1. So, this is now RLC circuit in parallel. Because of this resistor, what will happen, that initially the when current pulse is applied, it will start charging, discharging, but at Rp it dissipates the your whatever charging and while discharging, and it decay the your oscillation. So, this decay in the oscillation, how can we sustain the oscillation? So, see, simplest way of sustain the oscillation, can we cancel out the Rp? How can we cancel out the Rp? I have a Rp, and if I will generate a resistance equivalent to the Rp has the same value, but the negative in order to cancel out. So, that total resistance will Rp minus Rp is equal to 0. So, can we generate a negative resistance? Yes, we can generate a negative resistance. How? We can use the active circuits. Here, if you can able to generate, if you can generate the negative resistance Rp by active circuits, any active components, we will take example of MOSFET, but in past there are a gun diode or various kind of impact diode. So, all these diodes were used which has a negative resistance, the which will generate the negative resistance, and this negative resistance you can cancel out and you can generate the oscillation. So, we will take one example how the negative resistance can be formed in a MOSFET. So, here we will see step by step how it looks. This is a M1 transistor, and this across the M1 there are a capacitor between gate and source and capacitor between drain and source, which is denoted by C1 and this is denoted by C2. Now, if we try to see the impedance between a drain and gate, what is the impedance looks like. So, here you can draw the small signal circuit. This is a capacitor C1, this is a GM into VGS, this is nothing but VGS, and you will have a C2, this is a C2. We are seeing the Vx here. So, this is a plus or minus Vx and current Ix is flowing in this direction. So, we can write a VGS which is equal to minus Ix by C1 S. So, this Ix if we see in the direction of Ix in this direction, then the reverse direction is flowing through the V capacitor C1. So, VGS is given by Ix by C1 S. So, we can write the total voltage which is a Vx. So, this Vx plus VGS equal to the current which is flowing through C2, that is nothing but a Ix by Ix minus Gm into VGS 1 by C2 S. So, now we add VGS equal to minus Ix by C1 S, you will get minus Ix by C1 S plus Vx equal to Ix, this minus will be plus Ix Gm by C1 S into 1 by C2 S. And if we take Ix by C1 on the right side and if we take Ix and denominator, so Vx by Ix with respect to S is given by 1 by C1 S plus 1 by C2 S plus Gm by C1 C2 S square. If we replace S is equal to j omega, we will get a 1 by j C1 omega, 1 by j C2 omega minus Gm C1 C2 omega square. So, this is what we want, this is a negative resistance and you can have a negative resistance that depends on the Gm of the MOSFET M1. So, your input impedance Z in, if you see the equivalent circuit of this, that has a negative resistance and the capacitor which is a combination of C1 and C2, C1 C2 by C1 plus C2. Now, what you need is to have oscillation, you need a inductor which is denoted as a L1 and resistor which is a Rs. So, your Rs in this case, because the inductor is always lossy, we already have seen the quality factor of inductor and the Q which is equal to omega L by Rs, where if it has a certain value of Q, that will have Rs, you can find out the value of Rs. So, this Rs, if it is equivalent to the Gm by C1 C2 omega square, then we will get oscillation omega oscillation which is 1 by L1 C1 C2 upon C1 plus C2. So, this is how we can use a tank circuit made up of inductor and capacitor to design the oscillator. So, what we need is we connect one inductor at the drain, a combination of inductor capacitor, and that will generate that will be the one oscillator. So, we will try to see that circuit. This is called a tuned oscillator, where this is L1, Rp and C1 which is in parallel. Now, this C1 is a capacitor mentioned, but there are many other capacitance of the MOSFET needs to also be considered while calculating the resonant frequency. So, if we try to plot the V out by V in for this tank circuit, it looks like this, where at omega naught you will get the maximum gain, that is given by Gm into Rp. So, if you try to see on this side, it is more inductive, and which is mentioned at low frequency L dominates, and your V out by V in is given by minus Gm into L1 S, that is a Z, Z of the impedance of the L1. At high frequency, capacitor will dominate, and C dominants, you will have a V out by V in, which is minus Cm by 1 by C1 S, and at resonance you will have a V out by V in, which is equal to minus Cm into Rp. So, here this in this circuit, in this circuit there is a if we try to see that you will get a 180-degree phase shift. Now, can we connect this V out and V in? We can if we connect V out with V in, can this oscillates? The if we try to see that it is providing 180-degree phase shift, but it will not have a complete 360-degree phase shift, and that no frequency is satisfying the Barkhausen criteria. So, in order to have the sufficient gain, because if it is satisfying the criteria of the phase shift, but if it does not have a sufficient gain, then you require one more stage, and that is a nothing but a cascaded 2 tuned amplifier in a feedback loop. So, now if we use a 2 amplifier, 180-degree and 180-degree, total is a 360-degree, and if it is connected back to back, it is called a cross coupled oscillator. And for cross coupled oscillator, your Gm Rp should be greater than your Gm into Rp square, because one gain is Gm into Rp of this and another is Gm Rp of this. The square should be greater than or equal to 1, and phase shift is it is already satisfying 180 from this and 180 from this, total is a 360. So, here if it is a single stage at a very high frequency, it is providing the total phase shift of 360, but for the desired omega naught where the gain is high, it is in this stage when the gain is high, it is not providing the sufficient phase shift and it does not sustain. So, we require a 2 stage, and this is called a cross coupled oscillator. This is a widely used oscillator, cross coupled oscillator in the literature and available. So, this how the negative resistance will be generated, we will try to see that how this cross coupled is also generating the negative resistance. So, oscillation frequency we can get which is equal to 1 by L1 CGS2 CDB1 and CGD. So, CGS, which is this capacitor, CDB1 means drain to bulk, and CGD gate to drain, and C1. Because the value of these capacitors are in femtofarad, if you want to add one more degree of freedom, then you can choose a C1, and if you want to oscillate at very high frequency, then you can only connect a inductor also. So, your Vxy means total voltage swing, which is given by if we connect the current source ISS, because if we try to make it as a differential amplifier to cancel out the common mode signal rejection, we can use the current source, and that will have the equal current distribution in the both the branch in the M1 and M2. So, the voltage Vxy is given by a 4 by pi ISS into Rp. So, if we try to see the one port view of a cross coupled oscillator, this all is connected to the VDD, and this capacitor C1, C2, Rp, L1, L1 if we consider is this DC because it is connected through DC. So, when we try to see the AC resistance, this we can write it down as a C1 by C1 by 2, 2 Rp and series resistance and 2 L1. So, what is the Z1 here? So, if you try to find a Z1 impedance, here your Vx which is equal to, so if you see the Vx which is equal to V1 minus V2. So, and you can get Ix which is equal to Gm2 into V2, and on this side it is a Ix minus Gm1 into V1. So, if we write a V1 and V2 in this, if Ix is equal to minus Gm V1 and Gm2 V2 because it is connected cross coupled, if you put this Ix minus Gm V1 Gm V2 in this equation where Vx is equal to V1 minus V2. So, V1, so we will get a Vx, V1 is nothing but minus Ix by Gm1 minus Ix by Gm2. We will get a Vx by Ix which is equal to minus 1 by Gm1 plus 1 by Gm2. So, total is a minus 2 by Gm. If Gm1 or Gm2 which is equal, if M1 and M2 is a identical. So, in order to have a oscillation, this is a 2 Rp. So, your 2 by Gm should be less than or equal to 2 Rp. So, Gm Rp should be greater than or equal to 1. In order to have a oscillation, that Gm Rp should be greater than or equal to 1. So, this is what is a cross coupled oscillator, and we will discuss about the voltage control oscillator in the next class. Thank you.